This is lecture 20 of our course on high performance computing. In the previous lectures, we had been looking at a new form of programming, which I called concurrent programming. This became of interest to us once we learned how the operating system, which runs on all the computers that we typically use, does support the idea of multiple processes, even coming out of a single program, suggesting that the operating systems provide support for the required communication between those processes in order to achieve their common goal, and that it might be in our interests to learn a little bit more about this, since it might be a way to improve the performance of our programs on such computer systems. So in this brief aside on concurrent programming, which we started in the previous lecture, I mentioned that concurrent programming describes a situation where the program that you are dealing with runs as more than one flow of control. And one way this could be achieved is by having more than one process, by the program that you execute starting by maybe doing a fork or more than one fork to create multiple child processes. So the program runs as more than one concurrent process. I had used the word concurrent before. We now understand that it's the same use of the word in concurrent programming. The general idea being that there is activity across multiple flows of control, which, as we now understand, do not happen at the same time on the one CPU, but from the perspective of the programmer, it may be necessary to think of them as potentially happening at the same time, for reasons that we began to see in the previous lecture. So concurrent programming, unlike the kind of programming we've been looking at before, has an interesting new programming challenge, and that is how to set up the cooperation between the many processes which are cooperating to achieve the common program objective. And we understood that this has to be provided by mechanisms, some of which may be available only through the operating system. And in general, these class of mechanisms would be known as the inter-process communication, or IPC mechanisms. And I gave you some examples of how processes could cooperate. For example, they could cooperate by writing and reading pieces of data in files which are commonly accessible between the processes. On the other hand, they could cooperate using an operating system mechanism known as a pipe, which superficially looks very much like what the communication between processes through files would look like, in that the communicating processes would be reading and writing from file descriptors in the case of the pipe. In addition to this, there was the interesting idea that processes could communicate with each other, passing values or sharing values by actually having variables that are shared, commonly accessible by the processes. And this was a deviation from our understanding of the need for processes to be protected from each other, which is why we talked about the operating system's support for address translation, virtual memory, paging, etc. But in the light of concurrent programming, the potential of using shared variables for inter-process communication is clearly worth looking into, which is why we suspect that operating systems provide support for this as well, for defining regions of the virtual address spaces which are actually common between processes. And this might be available through some form of a shared memory control facility through an operating system. In addition to this, I raised the possibility of processes being able to communicate through operating system provided mechanisms called message, passing, and receiving. So one process could explicitly send a piece of data to another process, which could explicitly receive it, and that would be known as message passing inter-process communication. And we also looked at the idea of there being situations where it may not be necessary for the cooperating processes to communicate values to each other, but rather it may not be sufficient if they can synchronize their activities. And that may be supported through the availability of certain synchronization primitives. Now we will be seeing more about message passing and synchronization primitives towards the end of this course. But in this part of the course, I spent some time beginning in the previous lecture on the complications that could arise if one is setting up concurrent programs and making the communication happen through the facility of shared variables. Just to make sure we understand the nature of the problem that could arise in dealing with shared variables, we looked at the very simple example of a two-process program in which there's one shared variable which is initialized to 0, and all that each of the processes is doing is incrementing the variable. And as I had pointed out last time, for a person writing such a program, it would appear logical to assume that since the shared variable x is incremented twice, the end result should be that x should end up at the value 2. But it turns out that this may not be what happens if one writes this particular code without taking into account the complications of concurrent programming. So to fully understand what was happening here, we viewed this piece of code not as x++, but rather as what it would compile into in, let us say, the MIPS1 assembly or machine language. And this is what we came up with. The variable x would have to be loaded into a register. From the register, the addition of 1 could be done. And from the register, the variable x could be updated in memory using a store word instruction. So the x++ is actually 3 machine instructions. So to understand how it could be possible for the value of x not to end up as 2, I'll step through this to make sure this is very clearly understood. Initially, the shared variable x has a value of 0. It is initialized to have a value of 0. So let me draw a box which has representing the memory location x in terms of the shared variable, and initially it contains a value 0. Subsequently, I have 2 processes, process P1 and process P2, which are both executing machine instructions corresponding to the C construct x++. Now let's assume that this, as we saw, compiles into the sequence of instructions load word, add, and store word as shown on the right hand side. In the right hand side, I am showing a slight deviation from the MIPS1 assembly language notation in that I am not showing the address of x in base displacement addressing mode, but this is slightly more readable in our current context since it clearly indicates that we are talking about loading the variable x, and we understand that this could be easily corrected using the base displacement address of the variable x. So let's assume that when this concurrent program made up of these 2 processes, after the initialization of x to 0, let's suppose the process P1 is the first process to execute on the CPU. There's only one CPU, therefore only one of them can be running at a time, and we're going to assume that process P1 is the one which is running. Now we do need to note that as far as this particular code segment is concerned, in addition to the contents of memory location x or the variable x, we do have to keep track of the contents of the register R1. And note that each of the processes will have its own perspective on what the contents of register R1 is. As we have learned, there's only one processor. It is shared among all these processes, only one of which can be running at a time. Therefore, the contents of R1 has to be viewed as being specific to a process. So I show 2 possible situations as far as R1 is concerned. The one on the left corresponds to what R1 should contain when process P1 is running, and the one on the right corresponds to what R1 should contain when process P2 is running. So we are starting by assuming the process P1 is running, and therefore the first thing that we'll do is we'll consider events along a timeline. Last time we learned about different possible timelines. In this particular case, we are trying to show on the timeline what activity happens on the CPU, and the activity could happen on the left side if process P1 is running, or it could happen on the right side if process P2 is running. And further, since we now know the name to give for that kind of time, I will more correctly label this axis not just as time, but as real time, as opposed to virtual time. And note, I could just as well have labeled it wall clock time or elapsed time, all of which are synonymous terms with real time. Okay, so process P1 is on the CPU and running. Let's suppose that it starts by executing the load word instruction. We know that the effect of this instruction is to copy the contents of the variable x into register R1 from the perspective of process P1. Therefore, the effect is to get the value 0 copied from memory into register R1. Now let's suppose that process P1 had been running for some amount of time prior to execution of the load word instruction, and it is at this point in time that the operating system, in its preemptive process scheduling strategy, chooses to context switch from process P1 to process P2. So this is where a context switch occurs. The effect of the context switch is going to be that one of the other processes, in this case process P2, is identified as the one which should run. Subsequently, the hardware state associated with process P1 will be stored somewhere in memory, and the process state associated with process P2 will be inserted into the hardware. In other words, the hardware register R1 will now contain whatever value R1 should contain from the perspective of process P2. So the picture on the right suddenly becomes the current picture as far as the processor is concerned. So process P2 now starts its execution on the CPU. Again, it may have been running before, but let's suppose that when process P2 resumes execution, it too is trying to execute this piece of code. So it starts by executing load word R1X, as a result of which the value in memory location X, which is the value 0, gets copied into R1. It then executes add R1, R1, 1, which adds the value 1 to the current contents of R1, which is 0, resulting in a new value of R1, which is 1. So R1 gets updated to 1. It then moves to the store word instruction, where it updates main memory with this value of the register R1, and therefore the main memory variable ends up at the value 1. Now let's suppose that once again it is at about this point in time that the process gets context switched. What's going to happen now? The hardware state of process P2 will be saved in memory, and let's suppose that process P1 is the ready process that is now selected for running. Then its hardware state will be loaded, and therefore the current content of register R1 will once again be 0, because that was the correct value of register R1 as far as process P1 is concerned. Now when process P1 resumes execution, it finds or starts running on the processor again. The value in register R1 will be 0. Process P1 has already finished executing the load word instruction. It therefore will proceed with the add instruction, as a result of which the current contents of R1, which is from the perspective of process P1 0, will be added to 1, yielding a value of 1, which will be the new value of register R1. And then process P1 will execute the store word instruction, where it will update the main memory with this value 1. The value in main memory is 1 right now. The new value 1 will be overwritten over that 1, and the net result is going to be that after both processes have executed the store word instruction, in other words, after both of them have finished executing X++, note that at this point in time process P1 has finished with X++, and process P2 has already finished with X++. Therefore, the net result after both processes have incremented the variable X is what we see on the right hand side. The value of the memory location is 1. Not 2 as we had suspected. Therefore, this has happened, as we can now understand, because of this interleaving of the activities of process P1 and P2 and the context switches that might occur in between, the net result being that the impact on the shared variables may not be what we had thought they were from our understanding of the program at the C level. The simple understanding that X++ executed twice will cause the value of X to go up by 2. Right, so the final value of X could be 1. Again, you should note that for this particular concurrent program, it's also possible that the final value of X could be 2. If the context switches that I talked about here had not occurred at these carefully managed points in time, then each of these processes would independently have incremented X, and therefore the final value of X could have been 2. But it is possible that the context switches could occur as I have outlined. And that is why I point out that the final value of X could in fact be 1. So this is an example of non-determinism. If I were to write this program in this way, this concurrent program, I would have no control over whether the final value of X would be 1 or 2. And it is not often the case that programs which produce non-deterministic results are of use to us. Typically we write a program which will produce results in a predictable way from the perspective of the data that we are providing as input to the program. So this is not always a desirable feature, the non-determinism of a program. Right, so this was a problem arising out of the use of shared variables, and I drew the moral that it is in fact necessary to synchronize the activity of processes when they are modifying shared variables, and that potentially one has to view the regions of a concurrent program where shared variables are modified or accessed in this way as the critical parts of the concurrent program around which some form of synchronization of the two processes in this example, P1 and P2, may have to be done in order to produce the result which I consider to be desirable, or the one for which I had written the program. Okay, so the particular synchronization requirement here, which would actually remove the problem that we had seen, is if I had marked each of these two critical sections, in other words the regions of code where the incrementing of X was being done by process P1 or by process P2, as a region in which I wanted a guarantee that no more than one process should be executing concurrently, which is where the term mutual exclusion comes from. In other words, I want a guarantee that within that critical section, whatever X++ compiles into, I will say, is the critical section, the region of code where a shared variable X is being accessed. We saw that this compiled into 3 statements. Therefore, the critical section would contain those 3 statements. So what we're saying here is the mutual exclusion requirement is I require that either process P1 could be executing those 3 statements or process P2 could be executing those 3 statements, but I don't want process P1 to be halfway through when process P2 enters that region of its program. Hence the term mutual exclusion. We want the processes to execute in critical sections mutually exclusively of each other. In other words, only one at a time. Now, it is conceivable to have operating system primitives or basic functionalities provided for this purpose, and one such is typically known as the mutual exclusion lock. Mutex stands for mutual exclusion, and lock is a word suggesting that it is a mechanism through which one can safely achieve this essentially by locking the entry into the critical section from one process if it is not safe. So the word lock is appealing in that sense. And I described the lock as having 2 function calls associated with it. One to acquire the lock, in other words, to be used before one enters the critical section, and the other to release the lock, in other words, to indicate that one is leaving the critical section and that another process, if it so desired, could enter the critical section. And we came up with this tentative mechanism for implementing a lock using an ordinary variable. And the idea was that until, if we viewed the implementation of the lock as working by ensuring that if the value of the lock is 0, that means that the lock is available. In other words, it can be acquired by a process which requests it. Whereas if the value of the lock is 1, that means that the lock is not available, meaning that it is not available, and a process trying to acquire the lock at that point in time should not be allowed to enter its critical section, and suggested this implementation. But unfortunately, in going through this implementation, along the lines of what we did with that simple piece of X++ code, we learned that this is not a correct implementation of a lock. But we did learn an interesting idea over here, the notion that in order to keep a process waiting until it became safe to enter the critical section, one could use this concept of busy waiting, where a process was essentially executing this piece of code, which I would like you to look at again. Is essentially a loop. Since it is executing no instructions or no statements within the loop, I show it as a one-line loop. But just note that this is what it actually means. It's a loop in which there are no statements in the body, but merely the checking of the condition. And as long as the condition is true, it keeps on executing this loop. In other words, it keeps on being busy executing 1 or 2 instructions related to this, whatever this compiles into. But it is really waiting for the value of L to change to 0. Hence, this kind of a loop would be called a busy wait loop. And unfortunately, we learned that this does not work. When we step through this in terms of its machine language instructions, and this is one possible compilation of that sequence of 2 C statements into MIPS machine language, we saw that a situation very similar to that with the X++ code could happen. In other words, process P1 could start with this sequence of code and then get context switched out, and then process P2 could execute all of the code successfully and then get context switched out, and then if control is transferred back to process P1, then process P1 could in fact execute the rest of the code successfully, and the net result could therefore be that both the processes seem to have acquired the lock and enter the critical section. What does this mean? It does not mean that locks are not a safe mechanism to make shared variables a good idea. It just means that this implementation of the lock is wrong. Now, in order to implement the lock correctly, it might be useful to have some hardware support. And one form of hardware support which is often provided in instruction sets is an instruction which may look like this. I'm going to describe one particular instruction which is sometimes provided. It typically goes by the name Test&Set. Now, as the name suggests, it's an instruction which will actually do 2 things. It will test or read the value of a variable, and it will also, as part of the same instruction, set or change the value of that variable. So Test&Set is the name of what we're going to assume that it's the name of a machine instruction, right? For example, it might be a MIPS1 machine instruction, and it has only one memory operand. It does not take operands. It does not take all its operands out of registers, but rather has one machine this machine instruction has one memory operand, which is the memory location which is going to be read and updated. What does this instruction do? Now I'm going to describe what this instruction does using this yellow code segment over here. I'm showing it to you in C, but just note that this is the functionality of the instruction test and set. So you look at this, there are 3 steps. In the first step, over here I'm referring to the memory operand of the instruction by the word lock. So this is the memory operand. So initially the first thing that it does is it reads the value of lock and remembers it. In C I would describe this by saying that it stores the value of lock into a temporary variable, but this is just to note that it's reading the value of lock. In the second step, it updates that memory location to the value 1. That is the set that we are talking about. And as a whole, what the instruction has as a return value is the value that was stored in this temporary variable, in other words, the old value of lock. So this instruction is updating lock to 1 and returning whatever the value of lock was before. That's what this is meant to achieve. Now the important thing about this instruction is that though it does these what look like 3 operations, it actually does these 3 operations as one. And the word which is used to describe this is to say that these 3 steps of the test and set instruction are done atomically or indivisibly. Right? And essentially what it means is all 3 of these happen as one operation, with nothing conceivably happening in between. Therefore, either all 3 of them happen or none of them happens. That's the meaning which we should infer. It's not possible for a process to execute test and set instruction and get context switched after it had done the first step of the instruction. That is not possible, and the guarantee is given by the hardware. So you can now see that this kind of hardware support is going to make the implementation of a mutual exclusion lock easier, because it gives guarantees that context switches cannot occur between these 3 operations. Now one general point. I mentioned the test and set instruction as an example of the kind of instruction that could be included in an instruction set in order to support the implementation of busy wait locks or synchronization primitives in general. It's only an example, there could be others. In general, instructions of this kind, which serve this kind of a purpose, would be described as atomic for this atomic indivisible property, read, modify, write. Because if you think about it, this instruction is reading the value of lock and subsequently modifying and writing, updating the memory location. Therefore, these are the important characteristics of the instruction, that the 3 steps that we saw are atomic, indivisible, happening as if they were one. Just as a closing note on this particular instruction, you may be wondering, you said that this instruction has only one memory operand, but how then does it return a value? And the answer to that is that if we were talking about a test and set instruction in, let's say, the MIPS1 instruction set, and there had to be a return value, the return value could be returned in a register. So the form of the instruction could be test and set R1 lock, and the return value register would then, the destination register would then contain the previous value of the memory location, which was the memory operand. Okay, now given such an instruction, how would we implement how would we implement the busy wait lock? Now, as before, as we tried to do with our simpler implementation a while back, we will assume that there is a variable, an integer variable, let's say, associated with the lock, and that this is the memory location which is going to be test and setted, or tested and set. The way that we'll interpret the value of the variable L will be the same as what we were doing up to now. In other words, it will be initialized to 0. If it has a value of 0, that means that the lock is available, and if it has a value of 1, that means that the lock is not available or in use. So we can now go ahead and try to figure out what has to be present in the acquire lock function and the release lock function. These are the 2 functions that concurrent programmers who want to provide support for their critical sections will have to use. And we're just talking about how these things could be implemented. So this is not something that we have to worry about as programmers. We just for our general awareness of what's happening in the computer system. So the releasing of the lock is very clearly easy. The release lock function will be executed by a process when it is getting out of its critical section. In other words, changing the situation from one where the lock was in use to one where the lock is available, which means that when the release lock function is executed, the value of L was 1 and now merely has to be set to 0, which can be done with a simple assignment. So release lock is easy. The lock will be set to 0 using the basically this L equal to 0 will amount to a single store word instruction, where into the variable L the contents of register R0 will be written. Just note that R0 is the MIPS1. I am using MIPS1 like notation here. R0 contains the value 0. This is another example where the fact that R0 contains the value 0 is useful. The alternative would have been I would have had to generate the value 0 in a register, which may have required many instructions, and once again I may have had a problem with a critical section, a series of instructions which are accessing the value L. So it turns out to be nice that we have a 0 available to us in the register R0. So this compiles into a single statement. Okay, now what about acquire lock? What do we want to do in acquire lock? Now we know that in acquire lock we want to busy wait. We want any process which executes acquire lock should be stuck in acquire lock, busy waiting, until the value of L has been successfully changed from 0, which means from a condition where it was available to a condition where it was in use. We are going to change the value of the lock L from 0 to 1 using test and set, but we want to have a busy wait loop because it is possible that when a process executes acquire lock, the value of L is already 1, in which case it can test and set L, which will not change the value of L, but there will be a return value of 0, and therefore there will be a return value of 1 if the value of the lock was already 1, and therefore that process should continue to busy wait until this is the case, that it has successfully test and set L from a value of 0 to a value of 1. In other words, the way that we need to do this busy waiting is test and set L, which will change the value of L to 1, but since it may have been 0, 1 or 0 before, we want to keep on testing and setting L until the return value of test and set of L is equal to 0, which means that the old value was 0. Right, so this is what the implementation would look like. We have once again a busy wait loop. So as long as test and set of L returns 1, we want to continue executing that loop. This is the busy wait loop. But as soon as the return value from test and set of L is 0, I want to get out of the loop. I have successfully satisfied this requirement. The process which gets a return value of 0 is the first which has found the lock available and changed its status to not available. Okay, so we can actually just make sure we understand what's happening by running through the scenario where, assuming that our implementation of acquire lock is what I've just described, while test and set of L and busy wait on this, and the implementation of release lock is what I have just described, set L equal to 0. What will happen if there are a lot of processes trying to acquire the lock? In this example, I am showing 3 processes. Now we need to start off with some assumption. So in each case, the process is going through the protocol of acquiring the lock before it enters its critical section, and then releasing the lock when it is done with its critical section. So this was meant to be the protocol for the use of the lock primitives. Now let's suppose for the moment that process P1 is inside its critical section. It was the first process which tried to acquire the lock. It successfully acquired the lock and is therefore executing in its critical section. And I'll also assume that the processes P2 and P3 are trying to acquire the lock in order to enter their critical sections. Now if this is the case, then what I will notice is that process P1 is inside its critical section, and both process P2 and P3 are executing the acquire lock function, which means that they are executing while test and set of L, the loop, the busy wait loop while test and set of L. Now what happens to process P2 or process P3? Now since process P1 had successfully set the lock, the value of the lock is equal to 1, and every time process P2 or P3 run on the processor, they attempt to test and set L. You'll recall that the test and set function, the test and set instruction will read the old value of the lock variable, which is 1, and that will be the return value of the call, and subsequently it will modify the value of L to 1, which is not really a modification because the old value of L was 1. Hence, as long as process P1 is in the critical section, both process P2 and P3 will busy wait on their loops, repeatedly modifying the value of L to 1, but always finding that the old value of L was 1 and therefore unable to escape from their busy wait loops. Right? So the lock we know that the lock is equal to 1 because it was set to 1 when process P1 entered its critical section. And further, that when processes P2 and P3 repeatedly execute test and set on L, they merely overwrite that 1 with 1 again. Now this situation will continue as long as process P1 is in its critical section. So note that both process P2 and P3 and any other processes which may be trying to use the same lock will all be blocked, or rather busy waiting, and unable to enter their critical sections because this implementation at this point seems to be doing the right job. When will this situation change? The situation can only change when process P1 exits its critical section. So after it finishes with its critical section, it will come to the release lock function. The effect of it executing the release lock function is that it sets the value of L to 0. It sets the value of L to 0 and it proceeds with its other activity, but the value of L is now 0. Now in the meanwhile, the next time either process P2 or P3 runs, it is still in a situation where it is running while test and set of L. And depending on which one of these happens to be running first, it will notice that the value of L which is returned by test and set of L is 0, and indivisibly, because it is doing so with the test and set instruction, will change that value to 1. And hence will get out of the busy wait loop, enter its critical section, and so on. So depending on which of P2 and P3 actually runs next after process P1 has set L or reset L to 0, one or the other of the processes will enter its critical section, and the other unfortunately will not find that the value of L has changed from 1. And the same will actually be the situation regardless of how many processes I have. I could have 100 processes all trying to acquire this lock, and the same guarantees will hold. Therefore, this actually seems to be a correct implementation in terms of the requirement that only one process should be allowed to enter its critical section if we use the protocol described. And in order to do this safely, we required a little bit of help. We needed that indivisible instruction in the middle of which no context switch was possible. Okay, now just continuing on the subjects of locks a little bit, the kind of lock which we have just seen actually goes by a few other names as well. Some people just refer to it as a mutex. You'll remember that the word mutex was itself just an abbreviation of mutual exclusion, which is essentially the requirement that we had in order to make the regions of our program where we access shared variables safe. The requirement was we wanted only one process to conceivably be in such a critical section at a time in order to avoid the kinds of problems we saw with the X++ scenario. So some people may refer to a lock of the kind that we just saw as a mutex. Others may refer to it as a mutex lock. Still others may refer to it as a spin wait lock or a spin lock, because the kind of busy waiting that we saw could be as well described as this spinning on a lock in terms of there's a very tight while loop, and you could conceptually view the process which is executing this while loop as repeatedly executing a very small loop which could be described by the word spin. And as I myself have used, it's sometimes referred to as a busy wait lock. So many terms for what is basically the same idea. Now there are other kinds of locks which could be used to achieve the same, which could be used for the same purpose. And some of them might be different in the way that they keep a process from entering its critical section. In the case of the busy wait lock that we saw, the mechanism that was used was the keeping a process running, executing on this loop until it became safe for it to enter its critical section. An alternative could have been that if it was found that it was not safe for this process to enter the critical section, then the operating system could be invoked to block that process. In other words, to put it into a waiting state. So what I mean by blocking is for the operating system to actually move that process into the waiting state, moved into the waiting state until the lock becomes available. Now, conceptually, one can see that there is a distinction between these two. In the one case, the process is actually keeping the processor busy, because a process which is busy waiting is executing instructions. There's going to be a test and set instruction, and after that there's going to be an instruction to decide whether or not to branch back. So at least 2 instructions. Depending on the instruction set, it could even be a few more. And in some sense, one could argue that when a process is busy waiting, it is not really progressing towards its objective. it is keeping the CPU busy, it is keeping the CPU utilization high, but it is waiting for the value of the lock L to change, and as long as it is busy waiting, in other words, as long as it is running on the processor, we know that the value of the variable L cannot change, because the value of the variable L can only be changed by the process which currently holds the lock. And therefore, in some sense, busy waiting is not a constructive activity. The alternative that is suggested in the lower half of the slide is that an implementation of the lock in which the process which could have been busy waiting, in other words, it's trying to acquire the lock, rather than spending CPU cycles executing test and set instruction, you could actually be moved by the operating system, the process, into a waiting state. And subsequently, when the lock becomes available, one of the waiting processes on the lock could be woken up. The difference between these two should be clearly understood. Both can be used to achieve mutual exclusion for critical sections. One requires operating system support. The other does not necessarily require operating system support. If you think about it a little bit, in order to safely implement the busy wait lock, what we needed was an instruction like the test and set instruction. In other words, an atomic read modify write instruction. And as long as the instruction set contains an atomic read modify write instruction like test and set, which is not a privileged instruction, then any user can write his or her own lock primitives, or the lock primitives can be provided as library functions rather than as system calls. Therefore, the upper option does not require operating system support, whereas the lower option does, since it involves changing the state of a process from the perspective of the operating system. And in that sense, there are different perspectives on how a lock could be implemented. But moving forward, there are other primitives which might be provided to provide support for the various situations that may arise in writing concurrent programs. And one of the more widely known primitives is something known as the semaphore. Some of you may have heard the term semaphore before outside of a computer science context, because a semaphore is the name of some kind of a communication mechanism that is used both between ships as well as, I understand, on air tarmacs, some kind of a flag-based mechanism to signal, for individuals to signal information to each other over distances. Semaphore flags are used. So the term semaphore comes from that origin. Once again, it's referring to some kind of a communication mechanism or synchronization mechanism in the real world. Now, I would like to talk about the semaphore a little bit because it is an example of something that is more general than the lock, than the simple lock that we have just seen. As I had indicated, we will be looking at synchronization towards the end of this course, but I thought it would be nice to give a few lead-in ideas right now. So the semaphore is more general than the lock, and I'll explain what I mean by more general shortly. When we talked about the lock, we found out that there were two operations. There was acquire lock and there was release lock, and we understand the ramifications of implementation of acquire lock. In the case of the semaphore, there are two operations which are referred to as the P operation and the V operation. People sometimes refer to the P operation as the wait operation and the V operation as the signal operation. You may be wondering why they're called P and V, and the reason is that the inventor of the idea of the semaphores in the context of interprocess communication made up these ideas. He was not an English speaker but a Dutch speaker, and the Dutch word for wait starts with P, the Dutch word for signal starts with V. But in any event, the operations are fairly well known as P and V today. I will use that notation rather than writing them down as wait and signal. Now, what is the since the names are P and V, I do have to outline what their functionality is. The names do not give away. Unlike release lock and acquire lock, the names do not give away any information about what these operations do. So I'm going to describe the functionality in terms of what happens when the P operation is applied to a semaphore S, what happens when the V operation is applied to a semaphore S. So S refers to a semaphore. At this point, we view a semaphore as being some kind of a data structure. Now, in the case of the P operation, we find the first thing that is done is it is checked to see whether S has a non-zero value associated with it, and if that is the case, then the value of S is decremented by 1, and control is transferred. In other words, return from the P operation happens. Right? So, if S has a non-zero integer value associated with it, then S is decremented by 1 and returned from P of S. What if S is not non-zero? Then what happens is the process which executed P of S gets blocked. In fact, it gets blocked until S becomes non-zero, and when that happens, when the process is restarted, what it does is decrements S and returns. So, essentially what the P, or we now understand wait operation, does is when a process calls P of S, then if the value of the semaphore associated with the semaphore is non-zero, then the value gets decremented and the process returns, and the process continues with successful return from the P of S call. On the other hand, if the value associated with S is 0, then the process gets blocked until the value of S becomes non-zero, at which point in time the process resumes execution and starts by decrementing S and returning, the same thing that it would have done if it had found that S was non-zero. Okay, what about the V operation? So, now we understand why this is called wait, because there is a blocking until some condition is satisfied. The desired condition is S being equal to 0. Okay, now what happens when the V or signal operation is executed on S? Basically, the value associated with the semaphore is incremented by 1, the opposite of what was happening in the case of P. And subsequently, if there are any processes which were blocked waiting for S, such as we saw could happen, then one of them is restarted, and when it is restarted, it proceeds as we see. So, in some sense, we understand why it is called signal, because it is an operation which can be used to signal that a process has, in some sense, finished with the use of the semaphore, and that incrementing the semaphore is a flag of having finished with the use of the semaphore. I use that description in the light of our discussion about the lock. In the more general sense, just thinking of them as wait and signal may make sense. Let us see. Okay, now let us just try to understand the semaphore a little clearer by using the semaphore to implement, in a sense, a solution to the critical section problem. Until now, we had used the lock to solve the critical section problem. The critical section problem was we want to ensure that processes execute in their critical sections mutually exclusively. In other words, only one at a time. Okay, now the way that I am going to suggest setting this up is, I am going to assume that the semaphore is initialized to 1. Note that what happens in P is that the semaphore gets decremented. What happens in V is that the semaphore gets incremented. Therefore, I am going to initialize the semaphore to 1. In other words, I am initializing the semaphore to a non-zero value. Now, what I will do now is, I understand that a process can bring the value of the semaphore to 0 by doing a P of S, and that it can bring the value of the semaphore back to 1 by doing a V of S. Therefore, the suspicion is that I can achieve mutual exclusion by surrounding each critical section by a call to P of S before the critical section and to V of S after the critical section, if I assume that I had initialized the semaphore to 1. So, that is what I will assume, that whenever I have a critical section in my concurrent program, it is preceded by a call to P of S and it is succeeded by a call to V of S. Okay, now let us see how this works. Now, let us suppose that I have a process P1 which is executing this code. What happens when it executes P of S? This was essentially what happens in, this is an expansion of my description of P of S. Remember, if S is non-zero, it decrements S and returns. In other words, it makes S equal to 0. Why do I add this comment? Just note that if S was initially 1, then by decrementing S, I am making S equal to 0. What if S was equal to 0? Then the process gets blocked until S becomes equal to 0, and at that point it decrements S from 1 and returns. Right? The block process until S is not equal to 0. Yeah, so then that is okay. Just looking back at the previous slide, just note that the process gets blocked until S becomes not 0. So, this does have to be corrected. Okay. So, now we understand that this is what happens when P of S is executed. What happens when V of S is executed? The semaphore gets incremented. So, it was equal to 0, it now gets incremented, which means that it becomes equal to 1. And any of the processes, one of the processes which was blocked waiting on this semaphore gets unblocked. So this is what happens as far as the process is concerned. Therefore, while the process is executing in the critical section, we understand the value of S is going to be equal to 0. And subsequently, any other process which tries to acquire the semaphore by using the same series of events, for example, if a process P2 tries to execute the same piece of code, it will find that it gets blocked until the value of S becomes non-zero. In other words, until process P1 increments the semaphore. Therefore, very clearly the semaphore can be used to do what the mutex lock did. Kindly note this correction to the slide. This should be not equal to 0. Now, I had mentioned in my introduction to semaphores that the semaphore is more general than the mutex lock, suggesting that the semaphore can not only do everything that the mutex lock or the busy wait lock can do, they can do other things as well. So let me just try to show you some examples of additional things that the semaphore can be used for. Okay, now let's just think of a simple possibility. In the example which we have seen using the semaphore, I talked about initializing the semaphore to 1 because I wanted to ensure that at most one process could be in its critical section at a time. What if I initialize the semaphore to 10? What would happen then? Now, once again, I'll just assume that I'm going to use this semaphore in such a way that I have a concurrent program with many processes, and that each of the processes will have some code. I won't refer to it as critical section code. I'll just refer to it as some code, which it might have a call to P of S before that and a call to V of S after that. So this particular semaphore may have been declared as semaphore S and may have been initialized to 10. In the previous example, the semaphore had been initialized to 1. Now, what will happen if I have a semaphore that's initialized to 10? Once again, the same piece of code gets executed. Remember, the definition of P of S and V of S is fixed. It's well defined. But now when the first process executes P of S, it finds that S is not 0, and therefore it decrements S. In other words, the value of S goes down from 10 to 9, and that process returns. What happens when the second process executes P of S? It also finds that S is not 0, therefore it decrements S, goes down to 8, and enters the piece of code. And this keeps on happening until 10 processes have successfully decremented S, at which point the value of S will be 0. And when the 11th process enters the picture and tries to decrement S, it finds, unfortunately, that, before it tries to decrement S, it finds that the value of S has become 0. And therefore, this use of the semaphore, note that I've used the semaphore in exactly the same way as it was used for the critical section. The only difference in the program is that the semaphore is initialized to 10. And the net effect was this is some kind of a facility by which I can allow up to 10 processes to execute in a particular piece of code, or up to 10 processes to proceed beyond the call to P of S and do whatever they're doing. And 11th process and beyond will be blocked until at least one of the 10 had finished and exited from that region of the code. So this is definitely something that is different from what the lock could be made to do. But that's not a very satisfying example, because it's not clear why I would want why I haven't actually given you a satisfying example of a situation where I would want 10 processes to be doing one thing or the other. So I'll actually go back to an example which I have talked about in order to show that the semaphore can do something more than what a lock can do. This example is an example I had when I first talked about concurrent programs. I talked about this scenario. I could have a situation where I want to multiply two matrices, large matrices, let us say, and I choose to do it as a 3-process program. One process reads the matrices in, another process multiplies the matrices, and a third process prints out or outputs the product matrix. And we saw that there was a synchronization requirement here. I didn't want process P2 to start doing the multiplication until process P1 had finished doing the reading. Further, I didn't want process P3 to start doing the output until process P2 had finished doing the multiplication. So there was the need to synchronize or hold back processes until another process had achieved some of its work. And we can do this using semaphores quite easily. So let me just illustrate how. So here we have 3 processes, and their assigned work is listed over here. Process P1 is supposed to read in the matrices that are to be multiplied. I refer to them as the matrix A and the matrix B. Process P2 is supposed to multiply the 2 matrices and produce a product matrix, which is supposed to be what is written out by process P3. And I'll just remind you that in this example, I'm assuming that the matrices themselves are possibly available in shared memory. So we're not concerned about the fact that they are shared variables. We're trying to understand something regarding the synchronization of the processes. Okay, now the requirement that I have is process P2 should not proceed beyond this point in its program until process P1 has reached this point in its program. That is the first synchronization requirement. In other words, it's only after process P1 has finished reading that process P2 should start multiplying. So there's one synchronization that we have to do over here. Now, how can we achieve this using semaphores? The way to look at this is the following. Now, the process which I want to cause to wait is the process P2. Specifically, I want process P2 to wait at the red line until process P1 has reached its red line. In other words, process P1 has passed the read A, B part of its program. So I want process P2 to wait, and using semaphores, the operation which I have that can be used to make a process wait is the P operation. The V operation cannot be used for waiting. The V operation merely updates the semaphore. Therefore, I know that I need to include a P operation on a semaphore. Therefore, I understand that I'll need to declare one semaphore, which I'll call S1, and that prior to doing the multiplication, process P2 will have to wait on that semaphore. So I include a call to P on S1 over here. Now, if process P does a wait on the semaphore, unless the value of the semaphore is 0, process P2 will successfully finish with the call to P. Therefore, it's necessary for me to initialize the semaphore to the value 0 if I'm using this particular semaphore for process P2 to wait. Note that if I initialize it to 1, then process P2, when it called P of S of 1, would decrement the semaphore and proceed to multiply the matrices prematurely. Therefore, it's important that I initialize that semaphore to 0. So what will happen? What will happen is the process P2 will be blocked inside the semaphore until the value of the semaphore changes. How can the value of the semaphore change? The value of the semaphore should be caused to change as soon as process P1 has finished reading the matrices. And I can do that using the V call to the semaphore, which will cause the value associated with the semaphore to be incremented. Therefore, I include a call to V on S of 1 at the appropriate point in process P1. And by doing this, I get the required synchronization. Process P1 will finish the will finish the reading in, and will then increment the semaphore. The semaphore had been initialized to 0, therefore the incrementing of the semaphore will cause it to go to 1. And any process which had been blocked on the semaphore, such as possibly process P2, would then get unblocked and proceed to the next step. I can use exactly the same kind of use of a semaphore for the other synchronization requirement that I have, which is that process P3 should not proceed beyond this point in its program until process P2 has finished multiplying the matrices. Now, can I use this semaphore S1 for this purpose? It's possible that I could, but to be absolutely sure that I'm writing this program correctly, I will use another semaphore for the synchronization between process P2 and process P3. The use will be exactly the same, but I'll refer to it as the semaphore S2. Right, so with this proof that the semaphore is more general than the lock, we know that there are different mechanisms that an operating system provides to support concurrent programming. And I will end today's lecture with just a brief summary on where we are at this point in time. We understand that in order to do concurrent programming in situations where there are shared variables, there may be a need to protect the regions of the programs which modify the shared variables with a mutual exclusion-like requirement, or to synchronize the processes in situations where one may have to wait until one of the others has done a certain amount of the work of the common objective. And typically synchronization or mutual exclusion primitives such as locks or semaphores will be provided either in the form of library functions, which could be the case for locks, for certain kinds of locks like a busy wait lock, or in the form of operating system functionality, which may be the case necessary in cases where the blocking of a process has to take place, such as in a blocking lock or in a semaphore, where by the definition of semaphores as in our lecture today, the P operation and the V operation on semaphores may have to block or unblock processes which require operating system intervention. And we will look at a little bit more about concurrent programming in the next lecture. Thank you.